6 days. Right now we're talking about sampling distribution and sample proportion. So in practice tomorrow should just be more practice about what we're doing. So I really don't have anything to add on notes tomorrow. Maybe I'll do an example. And then on Friday, we're going to change, instead of talking about yeses and no responses. So what happens when the response is a number and therefore a sample mean? Stat E. So stat E 8.1.2 sampling distribution of sample proportions day 2. Disclaimer. To answer the questions at the end, to answer the final question, we are going to have to use normal CDF. Okay? So normal CDF is a part of the assignments for this unit. So even though we covered that was one of the main reasons why we learned about normal CDF in the normal model. You're going to use normal CDF this unit. That's the bad news. The good news is that once we leave this unit and we go to unit 9, you're not going to need to use normal CDF anymore, because the calculator has normal CDF built into what we want to do. All you will need to do is let the calculator know what the information is, and then behind the scenes, your calculator does normal CDF. Yes? Mm-hmm. Mm-hmm. From the, let's say there's 10,000 students. So I'm sampling 200 students at random for the 10,000. Or let's say there's a million students across the country. There's a million students, and I'm going to sample 200 students from the million. I'm sampling 200 students, and I'm recording their responses. How many people say yes? How many people say no? And that gives me a p-hat. That's one time, and then I'm going to do that 10,000 times. Really far. Pencil sharpener? Oh, I don't know. I thought I saw a pencil, like somebody had left one behind somewhere. I do not have a pencil sharpener. There might be pins in that box. That would be the best thing. That box that's on the floor. That box on the floor. That white one, yeah. All right. So in this unit, our parameter of interest, our parameter of interest is P. The proportion of the population and I'll put population in quotation marks like I did yesterday, who are successes. So in the example that we were doing in the do now, our population was all students, was high school seniors, okay? That's my population. And the successes, so it would be the proportion of high school seniors who are wanting to stay an extra year. Okay? So that would be because my success means that they say yes, that they want to stay an extra year. My statistic that I'm going to use, that I'm going to use to estimate the parameter is P hat. The sample proportion who were successes. So I sampled 200 students. What proportion of those 200 students said that they would want to stay an extra year? Now remember, there's that little subtle tense that I use. So the population, what does the population like? What are the population? What were the sample? Because the sample we know. The sample was taken. We know what they responded. But the parameter, we don't know. As a reminder, p hat is calculated by taking the number of successes divided by the sample size. So x represents the number of sample successes, and n is the sample size. And that gives me a p hat. When I divide, and that's kind of what you were doing in the beginning of your notes. Now, what's important to understand here, and one of the major things that we need to do, is we need to understand that if certain conditions / assumptions are met, then the sampling distribution of sample proportions is approximately, and I'm going to change the color actually, is approximately normal. Okay? And the mean will be equal to the true proportion, and I'm going to put, and we're going to use this, the subscript. The mean of the sample proportion is p, and the standard deviation of p hat is, and here's the formula we saw yesterday, but I didn't go into much, the square root of p, 1 minus p, over n, where n is inside the formula. Now, if you're wondering why, this should look kind of familiar to you. When we did the mean of x, it was n times p, but remember, to get p hat, we divide by n. So the mean is just the mean that you calculated before, but divided by n. So n's cancel each other out, you're just left with p. The standard deviation used to just be the square root of p, n minus p. That was the standard deviation. Now, but when I divided by n, or it was np inside here, but when I divide the whole thing by n, there's some math in here that the ends, this comes in, this becomes n squared when it moves inside the square root, and then therefore one n cancels out with another n down here, and you're left with this formula. I don't want to go too much in it, just know that that's the formula there. But basically that we're taking the binomial mean and standard deviation, and we're dividing it by n. That's all, that's how we get this formula. Okay, now I said if certain conditions, right? If certain conditions and assumptions are met. Now, in your homework, you have 3 problems where you're going to be checking the assumptions and conditions. Okay? You're going to check, do these hold? And 9 times out of 10, the answer is going to be what? No. Do the condition, are the conditions met? So 9 times out of 10, the answer is going to be yes, the conditions are going to be met. But you need to show me why those conditions are met. Kind of just like we did on the previous exam with the binary and normal. You have to show me why. Now, I could throw in a question that where it's not met, and I'm just saying, show me that. But if there's a follow-up question, so I'm going to give you 3 scenarios where you have to do it. In 2 of those scenarios, have a follow-up question. You can be guaranteed that those 2 are met so that you can do the next problem. That first one could be yes, could be no. Okay? So what are the conditions? So there are 3 assumptions and conditions. There are 3 assumptions. We call them the assumptions and conditions. And as a way of remembering them, they are S-I-N, sin. That's the best way to remember them. I mean, there's many different ways to remember them, of course, but there's 3 conditions, sin, for any sampling distribution. The S stands for sample is random. So the first thing we want to do is we want to have a random sample. Now, for the most part, you'll see me and I'll say there's a random sample, or we have to make sometimes we'll just say, okay, so we would assume that the first two are met unless we see something that says otherwise. So if nothing mentions that the sample is random, we're going to assume that it was a random sample. Okay, so does that make sense? Mm-hmm. You're going to say, I'm going to assume that it was a random sample, even though because it just didn't say it. I'm going to assume it was. There's nothing in the problem that says it wasn't random, so I'm okay to proceed. The second one is independence. Or it is what is called the 10% condition. And it's usually the 10% condition that we do, which says that the sample size n is less than 10% of the population. Now, this one is a little bit interesting one. Inside your activity, you'll see why this is important. Basically, what this condition is for is when you are sampling, in the real world, we're sampling from a finite population, okay? There's, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 students in the room right now. And if I know that there's like a 20% chance that you're going to say yes, or 30% chance you're going to say yes to whatever the question is, what happens is that when I select one student and I get their response, the probability of the whole class has now changed. Because only 20% of you were going to say yes to start with. Maybe there's only 3. But when I select one student, now the probability has technically changed. When we talk about larger samples, the idea is that as long as we sample less than 10%, even though the probabilities kind of change and the probability is not the same every single time, it's so insignificant that it doesn't change the math. It might change the answer to like 8 decimal places later on, but for all intents and purposes, it's not going to change the probability from one selection to the next selection to the next selection. Although they are actually minutely different, mathematically they're the same. And that's something that's a little interesting thing to do. A lot of times the reality is that if it's random, in this one, I almost like, and I didn't say this to the other class, I kind of put a star right here because if, like, we just assume that one. We just move on. Random, and then the last one is what's really important. And this is that this is the normality check. Okay? This is the normality check. Now, when covering sample proportions, the sample proportions, when we do the normality check, okay, it has a specific name. Now, when we do sampling means, the normality check is different. Does anybody remember what the normality check is? This is the same normality check that was on your previous examination. What is the normality check that we do called? No, the normality check. That was like, remember when we took the exam and it was like, check to see if you can use a normal model? The success and failures condition. Okay, which is that n times p must be at least 10, and n times 1 minus p must be at least 10. So that's the normality check for proportions. Should I expect at least 10 people to say yes in my sample and at least 10 people to say no in my sample? As long as you get at least 10 are expected yeses and nos, the distribution will be normal. Now, if you have further questions about why this is true, when I open up the slides, those slides 9 through 12, a couple of them actually are investigating this. So if you want to kind of see what happens when it doesn't, play with that part in there. It's a little bit extra if you want to go deeper inside of it. It'll show you a little bit why that 10 number is kind of important. All right, so if all of these conditions are held, boom, normal. So let's do it. So if all of these hold, I want to kind of give you an idea. So if all of these hold, basically what it means is that when I take my sample proportions, and I know it's going to be a lot of little p hats that you're drawing, and I take p hat and p hat and p hat and a 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 p hat. So just like when we were doing in our do now, if I take all of these p hats and I were to graph them on a number line, the distribution would come out to be approximately normal. Now, in reality, what we're saying is that the theoretical sampling distribution is approximately normal. And the theoretical sampling distribution is every possible combination or every possible sample of size n from the population. Now this is where, like, and I'm going to tell you the truth. I've taught AP statistics for quite some time. I taught AP statistics for 12 years before I didn't teach AP this year. And I would say that in my first 10 years of teaching it, I never personally even understood what the theoretical sampling distribution was. I had never really, in terms of it, never come around to it. And I was very surprised, and myself, along with many other AP teachers even, did not truly understand what the theoretical sampling distribution was. And I found out, and once I learned it, I was like, wow, that makes total sense now. That makes a lot more sense. What we did when we pressed that button and it gave me 10,000 samples, that's called a simulation, okay? We simulated the sampling distribution. That wasn't the actual sampling distribution, the theoretical sampling distribution. The sampling distribution is literally every single possibility that there is known to man. And the number is mind-boggling how many possibilities there are. It is a number that is incomprehensible, that even a computer might take days or weeks or years to actually do it. That's how big it is. Let me show you an example here. I'm going to start small. Right here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 13 students. Let's say I wanted a sample size of 5. Okay? I'm going to take a sample of 5. How many different ways from the 13 of you do you think that I could take a sample of 5? Just give me a random guess in terms of it. How many different ways in here can I take a sample of 5 students from the 13 of you? What do you think it's about? No wrong answer. Just give me how many different ways do you think I could do that? Do you think just 4 ways? Okay, 3 ways. Let me show you one example. Here's one sample of 5. 1, 2, 3, 4, 5. These 5 students there. That's one sample. Here's a different sample. 1, 2, 3, 4. And Natalie. That's a different sample. That's a second one. Here's another one. 1, 2, 3, 4. And Lorena. That's a third sample. 1, 2, 3, 4. And Mal. That's another sample. These are all different samples. Well, I can also do right here. 1, 2, 3, 4, 5. That's a sample. 1, 2, 3, 4. And then Mal. That's a different sample. How many different ways can I get a sample of 5?
Like 20. 10.
It turns out, math, this is a combination number problem. The answer is 13. Choose 5. There's 1,287 different ways. And that comprehension is very hard to grasp, because it doesn't seem like you thought it was in the teens. Maybe you could think of it, maybe make 100 different ways. Over 1,000 different ways that I can pick 5 of you. There are over 1,000, there's 1,287 ways that I can select 5 students from this class, and it would be different, that each group would be different. The theoretical sampling distribution would be the proportion, the p hats that I collect would be 1,287 p hats that would be graphed. That'd be every single possibility. Now that was only with a sample size of 5 from a population of 13. What happens if I had 100 students? All right, math, prob 3. What happens if I had 100 students and I took a sample of 5? How many different ways, how many do you think that's going to be? How many ways can I make a sample of 5 from 100 students?
10,000, 100,000. No.
1, 2, 3, 1, 2. 75 million ways.
What?
75 million ways. What happens if I was sampling 20 students? What happens instead of sampling 5 students, I sample 20 students from 100?
5 billion.
No, it's even bigger than that. This is 5 followed by 20 zeros. This is like a trillion. Or this is like a million trillion ways. The theoretical sampling would be that many. Now, going again what I said before, what happens if there is 10, let's say there were 100,000 people, 100,000, and I go about and I sample 200 students. What we did in our Desmos was we simulated 10,000 of these responses, because in reality, the calculator says, I can't even comprehend, my calculator cannot even comprehend how many of those are. There is so many, it is an uncalculable number. It's like 1 followed by, I believe, probably like a trillion zeros. That's how big it is. It is it would take literally even a computer of a high processing, it would never be able to actually plot the theoretical sampling distribution. That's what so what we do is we do simulation. So I hope that kind of gives you an idea of how big it actually is. All right, so let's do an example. Here's the example. All right, we have some data from the school, all right? And we have found out that 22% of students have been found to skip at least one class the past week. One class a week. So, have you skipped a class? Did you skip a class last week? About 22% of students said yes. Okay? Or we looked at the data and 22% of students were marked present for school but absent for one of their classes. 22% of students skipped at least one class in their previous week, each week. Okay? We randomly select 80 students. A, describe the sampling distribution of the 80 students. Sorry, the sampling of the sample proportion of students who skip at least one class a week. Okay? So in order to do that, we need to check the conditions. We need to check sin. Okay? So first and foremost, the sample is random. So check. All right? We will assume independence. There's no reason to believe that one student skipping, here comes the question. If one student skips, is another student likely to skip? For some of you, the answer is yes. Does that make sense? So it wouldn't be totally independent. However, it is reasonable that 80 is less than 10% of all high school students. And that makes sense though, right? So even though it's not truly independent, 80 is less than 10% of all students. And finally, the normality, check. N times P would be 80 times 0.22, which gives me 17.6. N times 1 minus P would be 80 times 0.78, which is 64.2. Both of these are at least 10. So check, check, check. So what is the sampling distribution? The sampling distribution, we can call it what? Approximately normal. Well, what's the mean? Well, the mean is P. Well, we have P right here, right? We know what P is. It's 0.22. And the standard deviation would be the square root of P, 1 minus P over N, which is the square root of 0.22 times 0.78 over 80. And if I punch that into my calculator, I get 0.046. So it is approximately normal with a mean of 0.22 and a standard deviation of 0.046. Sorry. P hat is approximately normal, follows a normal distribution, 0.22, 0.046, first mean and standard deviation. That's describing it. And now we go back to Unit 8 question. The next questions are now Unit 8 question. I'm going to do just one question and then I'm going to call it a class. B. What is the probability that at least 16 of the 80 students, of the 80 sampled, skip at least one class a week? So I sample 80 students. What's the chance that at least 16 of them say, yeah, I skip at least one class? What's the probability that at least 16 of them are going to say yes? Okay. Well, this is tricky here because my P hat here is actually 16 over 80, which if I do my math is actually 0.20. Okay. 0.20 is my number that I have to use. So just like we did before, we're going to make a quick sketch. We're going to make a quick sketch. The center is 0.22, and I want here's 0.20, and at least means I want the area above 0.2. This is what we spent all the last unit on. Now it's coming into play. So normal CDF 0.20, comma 9999, comma 0.22, comma 0.046. Now I did say that very quickly because that's what we did beforehand. And you should understand by now that 0.22 right here represents the mean. The 0.046 is the standard deviation that we just found in the previous piece. And this is telling me the area above 0.2. Clear. Second, vars 2.2, 9999, 0.22, 0.046, paste, enter. 0.668. 0.668. That's about 76% chance. So this is interesting. There is about a 67% chance, and it's just tricky because a lot of students don't understand the difference between probability and proportions. Two different things. There's a 67% probability that at least 20% of the students sampled will say they skipped. At least they skip classes. They skip at least one class. All right. There's about a 2/3 chance that I'm going to get at least 16 students that say, yeah, I skipped last week. I skipped the class. I cut. There's a 67% chance that at least 16 of them, that means 16 might say it, 17 or 18 or 19 or 20, 21, 20, all 80 students might say they skipped. That's possible. Very, very unlikely that all 80 say, but that is a possibility. And that's what we're doing. So going back into your actual Desmos, like I said, I'm unlocking it in here. I want to note that slide 9 is just what we wrote in our notebooks. It's a little summary of what we did in our notes. Slides 10 and 11 are there to help you understand why that normality check is actually working. Okay, that's slide 10 and 11. Slide 12 is a little bit of summarizing what is the difference between a sample distribution and the sampling distribution. Okay, the sample distribution would literally be how many people said yes and how many people said no. The sampling distribution is all the p-hats that are calculated from all those ones. Homework starts at slide 13 where you're doing a matching. So which one describe a sample distribution versus sampling distribution? Then really where the homework is, slide 14, I've given you a scenario. Check the assumption conditions, check sin. How does this apply for sin? And yes or no. So is it normal? Or not? The answer might be not, it might be yes. I am not telling. It is one or the other. Now, when we go on to slide 14, the answer is going to be yes to normal, but you have to tell me why. Because then I have a couple of follow-up questions. What is the mean? What is the standard deviation? And then these two problems are normal CDFs, just like we did. And then, again, this answer is going to be yes. Tell me why. And then you have some questions here, once again. What's the mean? What's the standard deviation? And then two normal CDF problems.